Hello everyone, in this video I'll be talking about why some algorithms perform better or just faster in general compared to other algorithms. So here I have a Rust program and it's basically running the Fibonacci function. So if you don't know what Fibonacci is, it's basically the sequence where the two previous numbers are added together to get the next one. So for instance, we start at 1, 1, 2, 3, 5, 8, etc. Right, so you can see how 2 is the sum of 1 and 1, 3 is the sum of 1 and 2, and 5 is the sum of 2 and 3. So how you see most people implement this algorithm is they use a recursive method, and this is really easy to understand how it works, because what we're doing right here is we're taking an integer n and we're basically adding the integer 1 before it and the integer 2 before it, as you can see down here. So we have n minus 1 and n minus 2. And then we always need a base case in a recursive algorithm. So basically, if n is less than or equal to 1, in this case 0 or 1, it just returns 1. So you can sort of see how this imitates the nature of the Fibonacci algorithm, because if n is less than or equal to 1, so at these indexes, n will be 1, and then otherwise you take the previous two numbers and you add them together to get the next one. So it's a very simple algorithm and it's really easy to understand, but as you can see, when I actually run the program, it takes quite a while. So right now I'm calculating 40 integers, or 40 indexes of Fibonacci. And as you can see, it took quite a while, and I can actually time it over here. So I can go time this program, and this is the same program as right here. You can see it's very slow, and it takes 4.5 seconds to execute, which is a very long time. But there's a way to make this algorithm better, and it's through an iterative method. So instead of using recursion, we do it iteratively, and at first glance it doesn't look that different. You're starting with two integers, 0 and 1, and then basically what you're doing is you're adding the first integer to the second integer, and you're setting the first integer to the second integer. So basically, if we start running through this algorithm, we start with 0 and 1, and then we make this temporary variable, and we set it to the second variable, b, and in this case it's 1. And then we add a to b, 0 plus 1 is still 1, and then we set a to temp, which is the old value of b. So basically you can see how we're basically setting b to itself plus the previous value, and then this is a new value. So the new value of b is the original b plus the value 1 before b, and it might be a little bit hard to understand, but that's basically how the algorithm works. It takes the current value, the previous value, adds them together to get the next value, and then it sets b and a to 1 after that, if that makes sense. And then we return b at the very bottom here. But as you can see, this algorithm is actually drastically different than the other one. If I just comment this line out, and then run it, you can already see the huge performance difference. It got to 40 indexes in a blink of an eye, and I can even crank this up to like 100. I'm pretty sure it'll still. Yep, it took probably less than a second, and I can even time this at 100 indexes. And you can see it executed in 1.28 milliseconds. 1.28 milliseconds, and this is running 100 cycles. As you can see, there's nothing different about the values. The values that are calculated are the exact same, but somehow this algorithm took 4 seconds just to calculate 40 values, and this algorithm took 1 millisecond to calculate 100. And if I change this back to the original algorithm, the recursive one, as you can see, once it gets past 40, it actually, the time it takes to calculate the next value just grows exponentially. You can see it starts stuttering at 41, going to take a couple seconds for 42, and then it's probably not even going to get past 50. Like, by the time it reaches 100, the universe will probably meet its heat death, right? So it takes an exponential amount of time to calculate the next value. But why is that? I mean, we're calculating the same values here. It's not any more, like, intensive on the CPU, or is it? So we're calculating the same values, but we're using two approaches. In this case, we're taking the first two values and we're adding them together, but in this case, we're just adding two values and putting it to the next one. So this function is actually runs in actually a different time complexity than this function, and I'll explain that right now. So we have two algorithms. We have the recursive. Sorry for my bad handwriting. I'm using a mouse. We have a recursive algorithm, and we have a We have an iterative algorithm. Yeah, again, sorry for my bad handwriting. But we have recursive and iterative. So what the recursive algorithm is doing is it's trying to find, let's say, Fibonacci of, let's take like 5 for an example, right? So Fibonacci of 5. So what does it need to find Fibonacci of 5? Well, it needs Fibonacci of 4 and Fibonacci of 3, right? It needs to calculate what Fibonacci of 4 is, the value 1 before it is, and it also needs to calculate what the value of Fibonacci of 3 is, the value 2 before it. But as you can see, this is actually very difficult to do, because to calculate Fibonacci of 4, you need Fibonacci of 3, and you also need Fibonacci of 2. And to calculate Fibonacci of 3, you need Fibonacci of 2 and Fibonacci of 1, right? And for each of these branches, you need like Fibonacci of 1, you need like Fibonacci of 0, Fibonacci of 0, and for this one, you need like Fibonacci of 2, and it just becomes a huge mess. As you can see, we're calling the same function over and over and over again, and as you can see, we're already calling Fibonacci of 2 3 times. Right, we're already calling Fibonacci of 2 3 times. We're already calling Fibonacci of 1 3 times. We haven't even done this one yet. This one goes to Fibonacci of 1. And you can see it's already hard to represent even what this function is doing, because it just takes way too many calculations, right? And as you can see, once we reach the base case, in which case the base case is when n is less than or equal to 1, when we reach the base case, we can just stop. So this one stops, 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 and so on. Right? So recursive is actually a very bad approach to the Fibonacci problem, because it needs to run through all of these. Now let's see what the iterative approach does. The iterative approach basically has A assigned to 0 and B assigned to 1. Right? And then what we do is we set B to A plus B. So we're taking these two values together, and then we're making 1, right? And then we set this to the new A, this to the new B, this to the new B, right? And then we're doing the same process again. So we're taking these two values, and then we're making the next one, which is 2. We change this to the new A, we make this to the new B, and then we do the process again. And as you can see, this is drastically better than the Fibonacci function, because this, we're calculating basically each value just once, right? We have 0, 1, 1, 2, 3, and we basically build a ladder to the function, to the index we wanted to get to, which is 5, right? So we're only gonna have to do this 2 more times, and you can already start to see how this is just so much better than the recursive method. because we're calculating each value once, and we're basically just climbing the ladder, right? Run by run, we're climbing the ladder. This one, it's like, alright, we're gonna make a ladder for this, we're gonna make a ladder for here, we're climbing these two ladders. But we also need a ladder here, we also need a ladder here, but then we need to combine these two ladders to get to this one, and then, oh wait, we need to combine this ladder, which is built off of these two ladders, and it's just a huge mess, right? So this is why iterative in this case is better than recursive. And there's something in computer science that we can actually use to describe how much better the iterative function is compared to the recursive function, and it's called time complexity. So time complexity is how much time an algorithm is going to use based on what n is, right? So in this case, we're using an n of 5, right? We're using an n of 5. And what we can do is we can make like a description of how long this algorithm is going to take if we plug in n, right? And if we go back to the iterative function, we can see that we're basically taking n, and all we're doing is a simple for loop. So we're looping through the values from 0 to n, right? So in total, we're going to loop through this function, we're going to loop through these steps a total of n times, right? The number of values between 0 and n is going to be n. So this iterative function has a time complexity of what we call big O of n, which means that as n increases, O increases linearly. So if we plot this graph, right, it's getting a bit messy here. Wait, hold on. Let me see if I can clear this real quick. Let me make a new, not a layer group. I want a new layer. Okay. Right, so we have our iterative function. We have our iterative function, and it's running in O of n time, right? And you can sort of think of this as a function like you would do in algebra or whatever, where basically we have O right here on the y-axis, which is basically the time, right? So this is the time. This is the time, and then down here we have n. And as n increases, O increases linearly, right? So it's basically just a straight line. You see if I can draw that better. It's basically a straight line, right? But what happens with a recursive method is it's actually running an O of 2 to the n, if I'm not mistaken. Right, and I can actually search this up real quick. Fibonacci recursive time complexity. And I can actually explain this in a second why it's to the n. Yep, it's O of 2 to the n. And this is because, as we saw before, we have like 5, right? And we need to find the value for 4, we need to find the value for 3, and then for the value of 4, we have 3. I'm just basically drawing the same diagram as before. 3 goes to 2 and 1. And basically, what's going on here is the number of function calls, right? You can see how, like, so 2 goes to 1 and 0. Hold on, let me draw this out. How do I move this? That work? Maybe not. Well, basically, so what happens is, we have 3 goes to 2 and 1. This 2 goes to 1 and 0. And if you draw this whole entire diagram out, you can see that there's a way you can calculate how many function calls that are made. So what you do is you take a look at basically how deep you need to go until you hit the bottom, right? And in this case, our depth is like our longest branch of this tree of all our function calls, right? If we find the longest branch, it's the branch going from 5 to 4 to 3 to 2 to 1, right? So we have 5 to 4 to 2, 3 to 2 to 1, which means our depth is going to be 5, right? But if we take a look at how many function calls are made in each like level or each like layer of this tree, right? If we take a look at how many function calls, we have 1 function call for this level, 2 function calls for this level, 4 for this level, and if we continue the pattern, if there was no base case, it would be 8 for this level and like 16 for this level, right? So if we ignore all the base cases, the number of function calls made for each level is going to be 1, 2, 4, 8, 16. So it's just a doubling sequence. And as you can see, 1 is just 2 to the 0. 2 is just 2 to the 1. 4 is just 2 to the 2. 8 is just 2 to the 3, and 16 is just 2 to the 4, right? So what we're doing is we have n levels, right? And we're basically adding 2 to the 0, right? We're adding 2 to the 0, which is the first layer, first depth, I guess, of the tree, right? We're adding 1 function call plus 2 to the 1, 2 function calls, plus 2 to the 2, right? That many function calls, and we're going all the way down to 2 to the n minus 1. As you can see, 16 is just n minus 1, right? 2 to the 5 minus 1. So 16 is just 2 to the 4, 2 to the n minus 1. So this entire expression shows us how many function calls are made in this entire recursive function, right? And if you do a little bit of algebra, you can actually see that 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 all the way up to 2 to the n minus 1, it's actually equal to 2 to the n minus 1. It's actually a really cool thing. It's actually really cool because what's happening is you have like 1, 2, 4, 8, etc., right? And this gets you to 12, 14, 15. This gets you to 15, right? But if we add another 1, to it, this actually gets to 16, right? If we didn't have the 8 here, this is 7, but we can add a 1 to it, it gets us to 8. Which means that if we add an extra 2 to the 0 here, or just 1 here, if we add an extra 1 to the sequence, we're gonna get 2 to the n, right? But since we're removing this 1, we need to subtract the 1 here, right? So this expression shows us how many function calls are made in this recursive sequence, which is 2 to the n minus 1. Now, you would write it as O of 2 to the n because in big O notation, you don't really, like this negative 1 right here, if n is like 100, that 1 isn't going to make a difference, right? It's basically meaningless. So we take out the 1 when we're writing big O notation, and we just get 2 to the n, right? So iteratively, our time complexity is O of n, which means that as n increases, the time it takes for the algorithm to run also increases linearly. But recursively, we're taking 2 to the n. Our time is 2 to the n, which means that if we plot the graph, this takes so much more time. If we have n right here and O right here, it's going to look like this. Or it's an exponential function. It's going to start out slow at first, but then it's just going to skyrocket, right? Because, 2 to the 100, right? 2 to the 100, I don't even know what that number is, but O of 100, I can count to 100, right? So this is the difference between the two algorithms, and why you should always be careful about how you implement your algorithms. And the main flaw in the recursive algorithm is you're just calculating the same value over and over again, right? You're calculating the value for 3 over and over again. You're calculating the value for 1 over and over again. In the iterative method, you're going through the rungs of the ladder, right? Forget the 0. 1, 1, 2, 3, 5. My handwriting is starting to get bad. 5, 8, etc., right? You're just climbing the rungs of the ladder, and it's just like you're just calculating 1 once. You're calculating this once. You're calculating this once. You're just climbing the rungs of the ladder, but this one you have to calculate the same value over and over again. And that's why the iterative method is so much better than the recursive method in this case. And that's also why we saw the iterative method get to 100 in 1.28 milliseconds, right? In 1.28 milliseconds. But in terms of the recursive algorithm, we're taking 4.51 seconds. That's like 400 times longer. Is that? No, more than that. I'm not sure how many milliseconds are in a second. But, yeah, it's taking like maybe like 10,000 times longer for this algorithm to run just to get to 40. And this one got to 100 in 1.28 milliseconds. And that's why some algorithms run faster than others. Thanks for watching, and I'll see you in the next video.